Okay, so in this problem, they're asking us to calculate the percent ionization, which means we need to actually figure out how much of it ionizes. That means we need to solve a Rice equation. The thing that I was talking about earlier is here you have a value of 10 to the minus 4. Here you have a value of 1. So the difference between these two is greater than 10 to it. And I'm talking about difference in terms of multiplication, not minus. The difference in the exponents. So then we can do this. We can actually work on the problem. We can construct a Rice table and calculate the concentration of hydronium ions, and then calculate how much of it dissociated, and then figure out the percentage. So if I do the Rice table and I can avoid the quadratic equation, then I get a concentration of hydronium ions of 0.0226 molar, and then I can calculate the percent concentration by dividing the amount that dissociated over the initial amount, 1.28, and multiply by 100 and obtain a percent ionization of 15%. So let's go and do that. Okay, so I have those two concentrations. So I'm going to start with the 1.28. Again, the 1.28 molar is telling me that right off the bat that I don't need to do a quadratic equation. If you have the time, please look up or if you know the equation, I want to ask you to tell me the equation for solving quadratic equation, because in here we have this is 10 to the minus 2 here, and this is 10 to the minus 4. So for the second case, we're going to need to solve a quadratic equation. Okay, so let's start with a simple one, then no quadratic equation. So we're going to say that the Rice table is going to be, let's do it here, HNO, NO2, dissociating to H plus, and NO2 minus. Notice that this time I didn't put the water, because the water kind of gets in the way. I don't need to write it for the Rice table, because I will ignore the water anyways. So I'm going the shorthand way of talking about H plus. Okay, so this is the reaction. The initial is going to be 1.28 molar. And so these ones are always molarity. I'm not going to put the units here either. So 0 and 0. The change is going to be minus x plus x plus x. And at equilibrium, I have 1.28 minus x and x. Again, products of the reactants, so the Ka is going to be the two products, x and x, divided by 1.28 minus x. And this value of Ka is 10 to the minus 4, which is more than 1,000 times smaller. 1.28 10 to the minus 3 will be 1,000 times smaller, so this is smaller, this is 10 to the minus 4. And therefore, I can say that this equals x squared over 1.28. It's going to be equal to 4.0 times 10 to the minus 4. The value of K x squared is going to be 1.28 times 4.0 times 10 to the minus 4. And then I'll have to take the square root. So let's do the x squared first. It's clear in previous calculations. 1.28 times 4.0, 10 to the negative. And I get to be 5.12 times 10 to the negative. So I need to take the square root of that. So square root of my answer from my previous calculation. And then it's going to be equal to, I'm going to put an exponential notation, 2.26.7 times 10 to the negative. Since they're asking us to calculate the percent ionization is going to be equal to 2.2627 times 10 to the minus 2 divided by 1.28 times 100. Yeah, and I get to be, I get a number of 1.76. Yeah, that makes sense. This is 10 to the minus 2 here. This is 10 squared, 10 to the 2, so those two cancel out. And then I have 2.26 divided by 1.28, so that's not twice as much as 1.28. Because 128 times 2 will be 2.56, is 2.26, so it doesn't go 2 times, but less than 2 times, 1.76. And this is percent. Okay, questions? I wonder how it compares to the answers. I'm afraid to look, but let's look anyways. Yeah, 1.77. I have 1.767. Yeah, they're right. It's 1.77. I did not round it up. I just dropped the decimal place. So let's take care of that. So let's erase that 6 and make it a 7. Because it was 1.76776. So breaking it there brings the 6 to a 7. And I don't know why I wrote a 7 to start with. Cool. Okay, so now let's look at the one that will need the quadratic equation. Does anybody remember what the quadratic equation looks like? So that should fit into, yeah, there we go. So that's the equation for the quadratic equation. How to solve. So if you have a quadratic equation, you have to start with let me just write here. That's right. Unit C that I'm writing. Okay, quadratic means that you have an expression that says ax squared plus bx plus c is equal to 0. You need to get your equation in this form, and then the coefficients of a, b, and c will go into the equation. So the equation, then the solution for the equation, there's going to be two solutions for that quadratic equation. One is going to be negative b minus the square root, and the other one is going to be plus the square root. So that's how you generate 2. And so here we have b squared minus 4ac. And this is a fraction divided by 2a. So that's the solution of the quadratic equation. Okay, so let's get rid of this one. I copy it here. And so we need to get to this equation here. So to get to this equation here, we need to propose the equilibrium. So we need to do a Rice equation now. So let's start again. This is for the 0.015. So we're going to have 0.0150 molar HNO2. And so the equilibrium is going to be the HNO2 dissociating to H plus NO2 minus. And here we have a 0.0, oops, this is a Rice, initial change in equilibrium. So 0.0150, 0 minus x plus x plus x, 0.0150 x and x. So the Ka expression is going to be equal to, this x times x divided by 0.0150 minus x. And that is equal to the equilibrium constant, which is 4.0 10 to the minus 4. 4.0 times 10 to the minus 4. So this is 10 to the minus 2. This is 10 to the minus 4. We cannot simplify it. And so we're going to have to go to the quadratic equation. So let's go into here and operate it. So we have x squared. I'm going to send this guy here, multiplying there. So it's going to be 4.0 times 10 to the minus 4 times 0.0150 minus x. And now I have, good, I have the equation, I need to operate this number. So I'm going to say x squared is going to be these two numbers. I'm going to multiply here. So it's going to be 4.0 to the minus 4 times 0.050. So this is going to be 6.0 times 10 to the minus 6 minus 4.0 times 10 to the minus 4x. So I'm multiplying this by that and then this by that. Okay, so I'm introducing the multiplier into the equation and I get this equation. Now I have to make it equal to 0, so I'm going to bring this 2 to the opposite side of the equal sign, which is here. And so this is going to be then x squared plus 4.0 10 to the minus 4 minus 6.0 times 10 to the minus 6. So now I have it on the ax squared plus bx plus c. So c is going to be this negative number, including the sign. So that's going to be c. B is going to be this positive number. And a is going to be 1. And make that more obvious. A is going to be 1. B is going to be this number here, positive. And C is going to be this number here, which is negative. Okay. So I now can go into solving the quadratic equation. That is going to be minus B. So it's going to be, let me switch back to my pen. Let's make it okay, so it's going to be minus B, so it's going to be minus 4.0 times 10 to the minus 4 plus minus the square root of B squared, so it's going to be that square, so B 4 times 4 is 16, 10 to the minus 8, so it's going to be 1.6 times 10 to the minus 7 minus 4, A, which is 1, C, which is negative 6.0 times 10 to the minus 6. And so that will be the square root of that divided by 2, and A is 1, so it's back to fixed. Okay. So now I have to operate this. So it's going to be minus, need a pen, negative 4.0 times 10 to the negative 4. Please, if I make a mistake, call me, just interrupt me. So this is going to be 1.6 times 10 to the minus 7 minus 4 times, this is going to be 4 times 1 is 4, times 6 is 24, that's a minus and a minus, so it's going to be 24 10 to the minus 6, or 2.4 times 10 to the negative 5. Square root of divided by 2. Okay, minus 4.0 times 10 to the minus 4. Now I can use my calculator to add those two numbers and take the square root of. So let's clear it, and I'm going to say 1.6 into the negative 7 plus 2.4 10 to the negative 5 Yep, so we have 2.416 10 to the negative 5, and we're going to take the square root of that. Square root of my answer. Okay. Okay. So I have equal to, let's do this. 0.00040. That will be 10 to the minus 4, 10 to the minus 4, plus or minus. And now I have 0.0049, 15, divided by 2. And now I can have the two answers. One which I add those two numbers, and the other one I subtract. So I'm going to add them first. So we have that number plus the negative of that. So I have to subtract that number minus 0.0040. And I get, so x1, the first, is going to be 0.04515. It's going to be positive, divided by 2. And the other one is going to be, I'm going to use a negative. A negative is going to give me definitely a negative number, and x2 then being less than 0 can be discarded because it changes, the concentrations can never be 0, and we said that x was the concentration at equilibrium. Discard it. Discard it. So this is the only useful result. So I'm going to divide that by 2. And so x then, there's only possible x, and that's 2.2576 times 10 to the negative 3. So I have then the value of x that I can use to substitute into here. Oh, I just made it. I just noticed a mistake. This should be an equilibrium is minus x. So it will be 0.015, 0 minus x, x and x. So let's do those calculations. So let me go back to green. So the concentration of the undissociated acid, HNO2, it was 0.015 minus x. And that is going to be 0.0150 minus 0.002576. So the concentration of HNO2, we can calculate it now by subtracting those two numbers. So 2257, and we will make this one, okay, so 0.0150 minus the answer that I got before. One is going to be 0.1274. And that's going to be, excuse me, I skipped a 0. So let me erase here. Here's that. 0.01274. Yeah. Molar. And the concentration of H plus is equal to the concentration of NO2 minus, and that is equal to 0.00226 molar. That is this number here, rounded to 3 significant figures. So the percent dissociation is going to be the amount that dissociated, 0.0026 divided by the initial amount, which was 0.0150, times 100. Okay, so let's go 0.002256, I'm taking this amount here more accurately, divided by 0.015 times 100, and I get 15.05. So 15.0 or 15.05 will be 15.1% dissociation. Notice here that the percentage of acid that has dissociated is larger for the weaker solution. So the weaker solution is this one here. So percent dissociation, percent dissociation. This is 15.1%, while this one was 1.77. So the weaker solution has a larger percentage of dissociation, and that is common and normal. So they're weaker, but they dissociate in a larger percentage than the more concentrated solutions. And that you can observe anytime that there is an equilibrium, an acid-base equilibrium. Questions? So let's review this quickly. Oh, have you lost my screen? Recently, I don't see. Usually it's highlighted. Can you see my screen, anyone?
Yeah, we can see it.
Yeah, I imagine so, because, well, usually there's a highlight around the screen that tells me I'm sharing it, and I don't see it. So that's what I asked. Okay, great. So you were too quiet to not have seen it. You would have interrupted me against unless you're extremely shy. Okay, great. So we found out that for the 0.150 molar solution, we needed to go through a quadratic equation, while for the more concentrated solution, we did not. So this one did not require, this first part did not require us to do the quadratic equation. The second part, for when we used the more diluted solution, we needed to use the quadratic equation. The quadratic equation is a pain. If you can learn how to, I'll try to show it on the screen, use one of these calculators, TI calculator, you can program your calculator to solve the quadratic equation. So the only thing you have to do when you do this is figure out the equation up to this point. Up to this point here, where you have, let me use up to this point, and you enter the values A, B, and C in your calculator, and the solutions will appear. So you don't have to go through these steps as we did here. It's not that bad, but again, it's a source of mistakes. So just make sure that you have, if you use one of these, to have a calculated programming. I don't know, you can use one online. You can probably find a site where you can enter A, B, and C and get the solutions. Remember that the numbers have to be, the concentrations have to always be positive numbers. So if you have one of the x's, in this case, like we said here, we were able to discard it because the concentrations have to be positive, and x represents the concentrations. Now, sometimes you'll have A minus x, B minus x, C minus x. So again, when you calculate your concentrations, you might get two solutions. The two might be positive. So, but when you introduce them and calculate your concentrations, one of those concentrations is going to be, one of those x values is going to give you a negative concentration once you operate them and calculate the concentrations like we did in here. Here. So when you do this, you'll get, if you get a negative calculation, that means that x value is not a solution. It's a mathematical solution of the quadratic equation, but it's not a chemical solution because concentrations can never be negative. In general, you're going to find out that the x is, one of the x is going to be positive, the other one is going to be negative in this kind of setups. Okay, questions? And I forgot to set the timer. I don't know whether we want to. So let me stop in here. I don't know how long has it been. I forgot to put my my timer on. So